So let's proceed. As you probably remember, the first time we discussed the general Lüroth problem and proved Lüroth's theorem, right? So today, in the first part of my lecture, I'm going to discuss the context of the context of algebraic geometry, which is related to this problem and this theorem. And then I'm going to turn to the main topic. So, the second part. From now on, we assume that K is algebraically closed and of characteristic zero. So we are going to talk about algebraic geometry. So assume we have an irreducible algebraic variety. Then we can consider the corresponding field of rational functions. All right. It's important to notice that the dimension of x can be expressed in terms of this field. So this will be just the transcendent degree of this k of x over k. Right? So maybe a standard example. If you take x to be Pn, so the projective space with dimension n, then the corresponding field is just the purely transcendental extension of the base field. So purely transcendental. Okay, then consider the following situation. So suppose we have two such varieties, x and y, and consider a rational morphism between them. So perhaps I would like to consider dominant rational morphisms. So dominant rational morphism. This corresponds to an inclusion of the corresponding fields of rational functions. K of y can be embedded into the field of rational functions on x. Okay, and also we can consider birational morphisms. Birational morphisms. Birational. This means that in fact we have an isomorphism of the corresponding fields. So k of y is actually isomorphic to k of x. Okay. Now let me define two notions. So x, so the first one, x is rational. X is rational if there exists a dominant rational morphism from some projective space to x. Oh, sorry. No. So this is the wrong definition. So here I need to take birational. So a birational. So birational morphism from Pn to x, which implies that in this case the dimension is actually equal to n. Okay, so a rational variety is a variety which is birationally isomorphic to the projective space of some dimension. There is also a closely related notion of unirationality. So x is unirational. This is given to the existence of a dominant rational map. And this is, of course, possible only in the case where n is greater than or equal to dimension x. Okay. So in the case of rational varieties, we require that this morphism be a birational isomorphism. Here we require only a dominant map, dominant rational map. So let's consider some examples, or maybe first some notes related to. So let's relate these notions to what is written here. The first one, x is irrational if and only if its field of rational functions is isomorphic to a purely transcendental extension of K.
Certainly, this variant looks much more natural than existence of rational models.
Okay. And x is unirational. So this means that K of x can be embedded into such a purely transcendental extension.
Maybe two comments.
Yeah.
Firstly, there is a concept in between, if you know.
Stably rational.
Sorry?
Stably rational.
Stably rational. Maybe it also makes sense to mention. And all three of them are non-equivalent, are non-equal to each other.
The result, actually, there are four related notions. So there is also rationally connected, so which is also close to this topic.
Which is not known as it is equivalent to unirational.
Okay. And let's of course notice that rational automatically implies unirational. So the unirationality property is a weaker one.
Maybe to say about stable rationality, just for education of existing present people.
Okay. X stably rational if and only if there is let's say an S such that x times e to the power s, so the projective space is rational. So there is also a related notion, but I will not need it in my lecture.
So rational implies stable stably rational, and stably rational implies unirational.
Yeah. Okay.
And one more comment. In this second point about unirationality, do you assume that this n equals the dimension of x?
Not yet.
But you will explain this.
I'm going to explain this, yes. So, examples. The first example, so let's consider the case of curves. So the dimension is 1. Then it's known, so there is a birational classification of such varieties of curves. So birational isomorphism classes. Birational isomorphism classes are parameterized by the so-called genus, by the genus g of x, which is a non-negative integer. And in this case, so it is known, so let me mention this as a fact. So x is rational. This is equivalent to x is unirational. And this is equivalent to the case where the genus is 0. And by the way, so the genus is 1. This is equivalent to the case where x is an elliptic curve, or in relation to an elliptic curve, which were discussed yesterday in Kirill's lecture.
So what do you mean by parameterized by the genus? There
What do you mean by
are the same genus which are not.
This is not true.
Sorry. Not parameterized, they just have, not parameterized, of course.
Curves with the same genus may be birational.
Yeah. Okay. So there is a, let me write it as there is a birational invariant. Called the genus. Yeah. So next I'm going to discuss more examples. So this was the first one. The second one. If you take G to be a connected reductive group, then we can consider, so it is well known that it has the so-called big cell, if you know. So it contains big cell, U minus TU, which is isomorphic to U minus to direct product. Right? And in this case, so U is a maximal unipotent subgroup, T is a maximal torus, and U minus is the opposite maximal unipotent subgroup in this case. So we have this direct product, and every unipotent subgroup is isomorphic to an affine space. So this is isomorphic. So these are isomorphic to AN. And T can be embedded into an affine space as an open subset. Some AM. And so we conclude that G is rational. G is rational.
This is one more equivalent definition of rationality. Contains an open subset, isomorphic open subset of a plan space.
Okay, yes.
Sorry, if there is u minus 1, it is u minus 1?
Oh, sorry. No minus 1, thank you. Just minus.
T can be embedded as an open subset.
Sorry?
T can be embedded as an open subset.
Yes.
Yes,
It's
as an open subset. Okay, now let's consider any linear algebraic group, maybe connected. Any connected linear algebraic group. Then we have Levy decomposition. So we have a Levy decomposition. So G is can be decomposed into a semi-direct product of, so this will be reductive, this will be unipotent, right? In this case, we can write an isomorphism of varieties, L times GU, and L is rational by the previous example, U is just again in a fine space, so we again get that G is rational. G is rational as a variety. One more example. So let's take again G, any connected linear algebraic group, and let's consider a homogeneous space of it. H, an algebraic subgroup. Right? And so, what can we say about the corresponding homogeneous space, G mod H? So we have a surjective morphism from G to G mod H. So surjective. So if you look at the definitions, you will see that this means that G mod H is unirational. G mod H is unirational. And finally, the last example. So let's again take G to be as above. And X, an irreducible G variety. Let's require G to have an open orbit. G has an open orbit. And so this again implies that X is unirational. X is unirational. Because actually, so this example is birational to the previous one. Right? Okay, so these were some examples.
It's good to say that G mod H need not be rational.
Need not be rational.
There are difficult examples.
Yeah. There are some examples where it is not rational, right? So actually, I'm going to discuss whether the converse implication is true. So in general, it is false, right? And actually, this is equivalent to the negative answer to this Lüroth problem. So let me let me write it here. So remark. Lüroth's problem is actually equivalent to the question of whether is it true that unirational implies rational. So if you compare this statement here with the definition, so you will see that actually this is the geometrical meaning of the notion of this Lüroth problem.
The value erased, I just say that it was called neuter problem. Thus, there exists a finite group of automorphism of a rational field whose field of invariant is not rational. And it was solved only in 80s. And this gives an example of non-rational homogeneous fields.
Okay, thank you. So, I have just erased the definition of unirationality, but the next lemma enables one to modify a little bit the definition. So, X is unirational. It has dimension n, so let n be its dimension. Then we can actually find a rational dominant map from the projective space of the same dimension. A dominant rational map from the projective space of the same dimension to X. So recall that in the definition of unirationality, we required n to be any, right? But it turns out that if there is a dominant rational map for some n, then we can also find such a map for the same n, which is the dimension, exactly the dimension of X. Okay, so let's prove it. Actually, the idea is very simple. So let me also write down the field theoretic interpretation. So K of X is actually embedded in this case into a purely transcendental extension of K. So the proof is uses a very simple idea. We can just successively reduce the dimension by choosing an appropriate hyperplane in Pn, for which the restriction of the morphism will be still dominant. So how to do this? So assume we have a dominant map from some P to X. So let's say n is the dimension of X, and suppose that this capital N is strictly greater than n. I'm going to show how to find a hyperplane in this Pn for which the restriction of the map will be still dominant in this case. So let U be an open subset such that the restriction of phi is regular. And of course it is dominant. We can choose a point x0 side x such that the dimension of its fiber will be exactly the difference of the dimensions, right? There is a general theorem on dimensions of fibers of homomorphism. So such that the dimension of phi to the minus 1 of 0 is precisely n minus n. We can also choose a smooth point inside this fiber. So take a smooth point in this fiber. And now, and now consider the tangent space of Z of this fiber at this point. Yeah, it has dimension n minus n. Now we can choose a hyperplane. Which contains Z and is transversal.
A smooth point for the fiber or
For the fiber, yes, for the fiber. So we choose a hyperplane which contains Z and is transversal to the fiber. So, and I claim that if we restrict our map to L, then we still get a dominant map. So formally we have, so let's see. So since it's transversal, so we compute the tangent space. In this case, we can bound it by what? N minus n minus 1, since it's transversal. Now, this means that the intersection of the fiber with this hyperplane has an irreducible component of dimension not greater than this value. Yes. Now assume that, so if we consider the restriction of phi to L intersected with U, so it is not dominant, so assume that it is not dominant. Then its image will have dimension at most n minus 1. Right? Okay, so the dimension of this L intersected with U is n capital minus 1. The image has this bound on its dimension, then all fibers of phi restricted to L intersected with U have dimension at least, so n minus 1 minus n minus 1, which is n minus 1. But still, one of the fibers, but the fiber over x0 is L intersected with. And we have already seen, so we have already proved that it contains an irreducible component whose dimension is strictly less than this value. So is it clear? So we've got a contradiction. So contradiction. So this means that the restriction, so this restriction is in fact dominant. So where is this restriction? So L phi restricted to L intersected with U is dominant. So we got L. We get a dominant rational map. So which is p to the minus 1, isomorphic to L, x. So in this way, we can reduce the dimension of the projective space by 1. So if we repeat this procedure, we can reach that the dimensions coincide. Right? So we can, so this lemma enables one to modify the definition of unirationality. So we can require that, so X is unirational if there is a dominant rational map from the projective space of the same dimension. Okay. Now, some corollary. So this is a general corollary in terms of the field theory. So suppose we have such a sequence of fields, and the transience degree of f over k is s. Then there are y1, ys, xn algebraically independent, such that f is in fact contained in an extension of degree exactly s. So this is again a reformulation of this lemma. And let me also state some further corollaries.
This is not a reformulation of this lemma, it follows from the proof. Because you can go to hyperplane, but formally from its lemma it doesn't follow.
Why not? So if we realize f as a function field on a variety, so this inclusion will give you a morphism, so a dominant rational map from projective space to this variety.
Then there is another projective space of dimension n, such that you may construct a dominant model.
Ah, okay. Okay, maybe so.
This is a corollary of the proof that you can go to a hyperplane section.
I see. Okay, thank you. So, of Lüroth's theorem. So which will be needed in the remaining part of my lectures. So again, assume we have such a chain of extensions. And assume that the transitive degree of f is exactly 1. Then we can combine the previous corollary with Lüroth's theorem and obtain that in fact this f is generated by a single element. So there is an alpha such that f is generated by this alpha. And again, so one useful consequence in algebraic geometry. So if we have such an x which is a curve, then if it is unirational, x is unirational, then we automatically have that x is rational. So in dimension 1, these two properties coincide. Actually, I told you yesterday that in dimension 2, there is also a similar result. And only starting from dimension 3, there are counterexamples.
The previous corollary falls under the assumption that K is algebraically closed.
Yes. So probably this can be generalized to some wider class of fields, but I didn't check it carefully. Okay, so let's proceed to the next part. So now consider the following setting. So let G be a connected inductive algebraic group. We fix a Borel cell group. Fix a maximal torus.
And this is the end of your story about unirationality.
Yes.
But maybe just to formulate the example how to construct unirational concentration.
I'm not ready to do it. So we can consider the unipotent radical of B, so let's denote it by Q. Also fix the character lattices, which are actually isomorphic. The character lattices of B and T. So now the main definition is that of complexity. So maybe X. So let's consider that X an irreducible G variety. Yeah, and let's define the complexity. The complexity of X is the value. It's the minimal codimension of B orbits in X. And actually, this can be also reformulated as the transitive degree of B invariant rational functions, or the field of B invariant rational functions, by a result of Roselind. So it's useful to give a remark that the case of complexity 0, so by definition the complexity is a non-negative integer, right? And the simplest case in this setting is that of complexity 0. According to the definition, this means that there is an open B orbit. So X has an open B orbit, and in this case, it is known. So there is a common name for such varieties. These are spherical varieties. So X is spherical. So this is the name of such varieties. Okay. Now I'm going to state the main theorem, which I'm going to prove in the remaining part of my lectures. So, theorem. Theorem of Knopf from 1993. So suppose X is normal and satisfies one of the two conditions. So condition A, it has complexity 0, and condition B, it has complexity 1 and unirational.
So some group Gx.
Yes, so X is an irreducible variety. So the complexity is 1 and X is unirational. Then the algebra of regular functions is finitely generated. So this is the statement. So in general, of course, this is not true. And also let me make some remarks about this.
So if X does satisfy one of these two conditions, then its algebra is finitely.
Yes, and one of A or B. Yeah. Remark. So these conditions, in fact, can be weakened. So if the complexity is 1 but X is not unirational, there is a counterexample. And also in the case where the complexity of X is 2 but X is unirational, there is also a counterexample.
Прошу прощения, может быть, теорема рабочая, конечно, что не самый пример.
No, K of X itself. So the algebra of regular functions on this variety.
So really this is a point. There are varieties whose algebra of regular functions are not finitely generated.
Yes, that's the point. So if you take an arbitrary irreducible algebraic variety, you cannot claim that its algebra is finitely generated. So this is false in general.
But if X is fine.
But if X is affine, so then by definition, so
But it's kind of don't make
yeah. So if X is affine, then we get finitely. So it is finitely generated by definition, more or less by definition.
Is it true for line bundles? So if we change the algebra of the functions on the global section system, so that's some line bundle X.
So I'm not sure, but if you can reduce to this theorem, then of course it will be true. So actually,
I'm going to discuss this counterexamples.
I'm not going to discuss because I wanted to pay much attention to the proof.
But how to construct this?
Actually, so this example is easy to construct starting from Nagata's counterexample to the Hilbert's 14th problem. So this is rather easy. This is not so easy. So in the article of Knopp, I couldn't understand it at once. So what is he going on? What is he doing? So in the remaining part of today's lecture, I would like to prove some lemma. So towards the proof of the main theory. So H, a linear algebraic group. So we can define and let's say be an H module. So consider an H module. Then we can define the set of H invariants. So which are vectors which are invariant. So HV equals V for all H in H. Yeah, invariant vectors. And there is also a similar notion of semi-invariant vectors. For me, it will be convenient not to include 0. So these are vectors for which the action of the group preserve the lines spanned by this vector. So these are semi-invariant. Okay. Now lemma. This lemma says that it's enough to prove the theorem for a subalgebra. So recall that we have this maximal unipotent subgroup. Suppose that k of x, so the U invariance is finitely generated, then the algebra of regular functions itself is also finitely generated. So this lemma gives us a reduction to a smaller algebra. Let me so let's write it like this, probably without. So the statement in the converse direction is also true, and this is and it's known as Avdeev's theorem. So in fact, so these are two equivalent conditions. And I'm going to explain the simple direction. I have some time. So, proof. So let's take F1, Fs, a finite generating system. So these are functions which are invariant with respect to the action of u. We can also require an addition. So we may assume in addition that all these functions are T semi-invariant. So each such function, so each u-invariant can be decomposed as a sum of such T-invariant, T-semi-invariant functions. So we can replace it by object components. Okay, so then they are B semi-invariant, right? And this means that all these functions are highest weight vectors in the G module of regular functions. So they are automatically B semi-invariant. This means that for every I, the corresponding G module generated by Fi is a simple G module. Simple finite dimension. Now, let's choose, so let's, for every such model, let's consider a basis of it. So let S be the union of basis of all these G models. So we may assume that each of these functions belongs to S. Right? And let's generate a subalgebra by this set S. So let's mention that this is a finite set. So we have a finite collection of finite dimensional G models, and in each of them we choose a basis. And then we take the union of these vectors. So the algebra K of S is finitely generated and G-stable. So this is finitely generated because it is generated by the finite set S, and it's G-stable because it is actually generated by a finite collection of G modules. And also, since it contains all the functions F1, Fs, and these functions are generators of the U-invariant algebra, then we get that such an inclusion. I claim that in fact we have an equality. assume these two subalgebras are not equal, then you can take a function for an element.
K of X result.
Sorry?
What proves that K?
Yes.
Not Q, without Q.
Without you.
No, I'm downstairs.
Downstairs. Yeah. So this is what I then there is a function, an element f, which is in kfx, but not in kfs. Right? Then we can generate a G module by this function. So this is a finite dimensional module, and this is a G-stable subspace, and it is not contained. It's not contained in KFS, right? Therefore, if we intersect with this KFS, this will be strictly contained in the G module. So we can take, since G is reductive, its representation on this G module is strictly reducible. So this is a G submodule. And we can find a complementary finite dimension G module. So there is a non-zero. Simple G submodule. And so it's not contained in KFS. So, or maybe so the intersection with KFS is trivial. Then we are almost done, because this module contains a highest weight vector which is invariant with respect to U. So then 0 is contained in KFX U, invariance which is contained in KFS. And so this contradicts this intersection condition. So contradiction. Okay, so this means that our assumption is wrong, and in fact we get the equality of all the algebras. So K of X is finitely generated. So this completes the proof. Yeah, I think it's going to stop.
Thank you. Any questions?
Here you use that if you have an arbitrary variety with a regular reductive group, then any regular function is contained in a finite dimensional G module.
Yeah, so this is rationality property for the modules.
For for integer variety. This is not completely obvious, but this is known.
Yes.
And what is your plan for this last lecture?
So my plan for the last lecture was to prove the theory.
Is that right? You need 1 hour to finish the proof.
Hmm?
You need 1 hour to finish the proof.
I hope it will be enough, but I'm not sure.
So there are counterexamples also. There are examples of varieties with non-finite generated regular functions. One can understand that there is such an example using Data's, for example. But maybe do you know some simple constructions? Maybe some variety. Do you know any simple examples of varieties with non-finite generated functions?
I'm not sure at the moment.
Or maybe some simple packages.
No, nothing comes into my mind.
There is a called risk construction, which was before Data, which produced such variety. And also there is a remarkable theorem by Winkelmann, that any algebra of regular of invariance is an algebra of regular function on some variety, on some quasi-affine.
Every what?
If you take, as far as I remember, take an affine variety.
Affine variety.
Take any action of linear algebraic sequences variety. Then the algebra of invariance is the algebra of functions on some variety, in some quasi-affine variety.
Okay.
More questions, comments? If not, then let's say